All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Tuesday, February the 25th, I believe is what today is. All right, today we're going to be talking about single and double replacement reactions and how to predict the products. So if you guys are liking these videos and just enjoying the learning experience that you're having watching these videos, be sure to hit that like button and subscribe to that channel. Alrighty, so here we go. We talked about single replacement reactions. We did a couple yesterday, the replacement of a metal by a more active metal. How do we know if one metal is more active than another metal? The chart. Okay, anybody know the name of that chart?
Periodicity.
No, that's that chart, but that's not the one we're going to use. We're going to use the one on page 278 in your book, and it's called the activity series. The activity series of the metals. Okay? Now, look, you're always going to have this. You're always going to have this. But you have to look at it. And we did the reaction yesterday of putting silver, or copper, into silver nitrate, and we saw that the silver formed on the bottom. The blue color, the silver nitrate kind of turned blue because the copper replaced the silver. And the way that I know that that's going to happen, okay, can I get this one out? Okay, so here again is the same type of reaction. It's real blue, and you can see all the silver coming off of that. So that's pretty much pure silver there, and then the blue color is due to the copper dissolving. So again, how do I know that the copper is going to replace the silver? Well, here's copper and here's silver. Copper is higher up on the chart than the silver, so that tells me that it's going to replace it. Okay? So then we did another one where we put zinc into copper sulfate. So if I put zinc into copper sulfate, the zinc will replace the copper. And again, this was the copper sulfate. And you guys did one in the lab very similar to this, but instead of using zinc in the copper sulfate, what did you guys use? Okay, look at your lab. If you have it out, look at your lab and look at reaction 3, I believe it is. What was reaction 3? Iron filings in iron copper. So let's find iron. So here's iron, okay? Here's copper. So what do you think happened in that reaction? Iron replaced the copper. So what did you observe on the bottom of that test tube? You should have some observations written down. What did you say? What did you see on the bottom of the test tube? On number 3?
Give me a second. It went black.
It what?
The CUSO. Is it the CUSO4 one?
Yeah.
I said it became blackish blue.
The solution did. Yeah. Did you say anything about the solid on the bottom?
No.
Huh? It turned orange. What substance kind of looks orangey? Copper kind of looks orangey, doesn't it? Okay? So you can kind of see that solid forming on the bottom. It changed from that iron, kind of a brownish rust kind of weird color, to more of a reddish orange kind of color, which is indicative of what element? Copper. Okay? So we're seeing that reaction taking place. Okay? Now, the second type of single replacement, I think we just barely touched on it yesterday, was the replacement of hydrogen in acid. Now remember, all acids have hydrogen, right? That's how we know that it's an acid. We're going to follow the exact same principle, though. Here's hydrogen right here. So in order for the metal to replace hydrogen, it's got to be above hydrogen on the activity series. So again, if I take Where's that graduated cylinder? If I take some 2 molar here's some copper. Here's some 2 molar H2SO4. Okay? That's the 2 molar means how concentrated it is. Okay? H2SO4, and I put some magnesium. Is magnesium more active than hydrogen?
Yes.
Yes. So if I go and I take some magnesium metal and put it into here. There's somebody at the door again.
It's Jackson
Well,
hates water.
Yeah. Okay? Just time to finish it. He's checking a little late.
Doctor's appointment?
Oh, okay. Yeah. All right, so I take the magnesium and I put it into the sulfuric acid, and immediately what do we observe?
Bubbles.
Bubbles. So what do you think those bubbles indicate? Okay?
Gas.
Gas is being produced, and what gas do you think it is?
Saline.
Okay? Hydrogen gas. Okay? Hydrogen gas. Now, by the way, what is that reaction taking place when it burns? What's this reaction? I don't think there's anything more. No. So we just said it's hydrogen gas. So what is the burning?
What is burning?
Yeah, but when something combusts, what does it combine with?
Oxygen.
Well, heat gets given off, or we need a spark to start it, but it's usually heat given off. But what's the actual reaction?
Oxygen.
When something burns, it combines with.
Wait, no.
It is exothermic, but I'm trying to say is when things burn, what are they combining with?
Oxygen.
Oxygen. So when the hydrogen's burning, what is it combining with? Oxygen. So what is it making?
H2O.
Okay. Well, don't laugh. Don't be silly, because that's the right answer.
Oh, is it actually?
Hydrogen and oxygen. I mean, duh. It's gonna make water. Okay. So all of that whoop is nothing more than hydrogen and oxygen coming together and making water. Okay. You didn't see it? Because it was steam, it was hot, it was water vapor. But you can kind of see it now condensing on the inside.
Do the gas again.
Okay? When here we decomposed the water into hydrogen and oxygen, but then I collected the hydrogen, lit it, turned it right back into water. Okay? Hydrogen and oxygen are always going to make water. Okay? That's the most common form of the hydrogen and the oxygen. So anytime we mix, so we saw that reaction here, but if I take a penny and I put a penny down into here, a penny is made out of copper, or at least got copper on the outside. Copper is here. Hydrogen is here. So what happens?
Hydro replaces the copper.
Well, the hydrogen is not going to replace the copper. So what's happening in here? Nothing. Copper is not more active. The hydrogen's already in here. Copper is not going to replace the hydrogen. Copper doesn't react with the acid because copper is not more active than the hydrogen. So you put them together and nothing happens. There's no bubbles being given off now on this one. So the metal has to be more active. So none of these metals, silver, platinum, and gold, make great jewelry because they're so low on the activity series, they don't react. Copper even being up here, if you have cheap copper jewelry, what happens to your fingers? Turn green, because copper compounds are green. Okay? So that's how you just kind of see. These very unreactive elements are what make it good jewelry. So it's the simple single replacement reaction. So if you go then in your notes.
So you wouldn't want to make a necklace out of lithium?
Probably not, no, because it reacts with water and it gives off hydrogen gas that catches on fire. So any sweat or any moisture on your body, you're gonna, and we're gonna see that reaction here in just a second. Okay, so if we look here, the replacement of hydrogen in metal. So we just did zinc plus sulfuric acid. What's the formula going to be for sulfuric acid? Sulfuric acid came from which anion? Sulfate. So we look up here and you see that sulfate is SO4 with what charge? 2 minus. So how many hydrogens do we add to it? So the formula for sulfuric acid is going to be woohoo! Look at that. That was like in multiphonic, polyphonic, not just stereo. There were too many for me to know how many it was. I like that. So we have zinc is above hydrogen. So the replacement of the metal must be more active. It's the replacement of hydrogen by an active metal. So what are we going to make? ZnSO4. But remember, what's the first step always in writing the formula of a compound? Writing an equation. Balance. The subscripts balance. What are we balancing though with subscripts? The charge. So what's the charge on zinc? What's the charge on sulfate?
What number is
Okay.
zinc?
Zinc is number 30.
Zinc is 2.
2. And then sulfate?
2 minus.
2 minus. So we don't have to do anything. But you don't just carry it over. You always balance the charge. Okay. And then what's left? Hydrogen is one of our 7 diatomics, and I know that that's a gas. Okay? Now, let me just tell you how to use this chart so we can know what state this is going to be. Okay, so Avery, follow me all the way to the back. We're going to shoot on that chart. Okay? So if we look at this chart right here, this is a solubility chart. Okay? This is a solubility chart. So here are anions. This row plus this row means it's soluble in water. Soluble in water up there is going to be what state? How do we represent something soluble in water? Aqueous, right? Okay, so this plus this means aqueous. Form soluble compounds. So most cations with nitrates, all nitrates are soluble. Anything that has a nitrate in it is going to be soluble. It's always going to be aqueous. So anything nitrate is aqueous. Okay? Your chloride, bromide, iodide, most everything are going to be soluble. Most chlorides, sodium chloride, potassium chloride, ammonium, those are all going to be soluble. However, this column plus this column means precipitate, insoluble, solid. So silver chloride is not going to be aqueous. It's going to be a precipitate. It's going to settle out. Okay? So this column plus this column is always going to be aqueous. This column plus this column, that's going to be a solid. It's going to be a precipitate in the reaction. Okay? Now, there's 3 big rules that if you can just kind of keep track. All nitrates are going to be soluble. Okay? Anything in alkaline metals, group 1, lithium, sodium, potassium, rubidium, anything in group 1, always soluble. And anything with, notice here, sodium, potassium, and other cations in column 1 and ammonium, most cations, there are no common things that are going to be precipitate. Okay? So if you know that all your alkali metals, ammonium, and nitrate, always soluble. The other thing's probably always going to be a precipitate. But you'll have that chart. Okay? You'll have that chart. So zinc sulfate. So now using that, everybody look. So you find sulfate, it's right in the middle of the first column. Most cations are soluble. The only sulfate that are not soluble are barium, strontium, lead, silver, and calcium. Okay? Is zinc one of those 5 over there?
No.
No. So that puts it into the most cations category. Okay, it's not a barium, strontium, lead, silver, or calcium, so that means it's going to be aqueous here. Now, before you stress too much about that, that is, of writing all this, that's the least important part of writing all this. Okay? But we're just going to keep working on that. So now if I take, I don't want to do the one in your lab.
Do the one in our lab.
No, I'm not going to do the one in your lab.
The one in our lab.
So if I took some iron and I put it into HCl, aqueous, iron solid. Is iron, anybody still have your book open to page 278, is iron above hydrogen?
Yes.
Yes, that means it would react. So what are we going to make? Okay, so now we're going to go to FeCl. Okay, but iron, when we look, well, what's the charge on iron going to be? So look on your periodic table, and I need you to look on yours because that one, yours is different than this one. Okay, on your periodic table, it can be +2 or +3. Okay, does anybody have it open? Okay, so Josie, is there either one of the 2 or the 3 bolded?
On which one?
On iron, element number 26.
Three.
The 3 is bold. So the bold means it's the most common isotope, not isotope, it's the most common oxidation state. So that's the one we're going to choose. Okay? You have choices, either one, but we're going to choose +3 because it's the bold one. So iron's +3. I'm going to say 3+. What is chloride always? -1. So what's the formula going to be of iron chloride? FeCl3. And then my other product is going to be H2, which we know is always a gas. Now, let's go ahead and balance it, then we'll figure out the state. 1 iron, 1 iron. I have 3 chlorines. I'm writing pencil though, so I'm going to put a 3 here. But now I have 3 hydrogens and 2 hydrogens.
Make it 6.
So I need to go to 6, which means I need to,
We need to make it 4.
well, I got to put a 6 here, okay? Which is going to give me a 3 there. But what else now just got messed up?
You have to put it
Okay? What, 2 where?
in front of Fe, in
2,
front of
6, 2, 3.
I need to put a 2 there and a 2 there. Okay? In order to be able to get that balance. Now, again, I can always double check, make sure you didn't just double high, I want to make sure it reduces. Yes, sir.
What would it be like if it was instead of Zn plus H2SO4, it was H2 plus ZnSO4, and then it goes to the right, like if it can't react, because it's
You just put no reaction.
on the right side?
Yeah. So in other words, if I put in copper, solid, plus I put it into H2SO4, but copper is not more active than hydrogen. So it just sat there, right? So you just put no reaction. Nothing.
Because it just sat there.
Yeah. Okay? So notice it's still following the exact same formula. It's A plus B plus AX is going to go to BX plus A. So I mean it's just the replacement of that positive thing. Now this is the fun one, the replacement of hydrogen in water by a very active metal. Really the only ones that do these are the alkali metals. The only one that are going to do those are the alkali metals. Okay? Right here, it's that. So, we're going to watch a video of this one. Now, we're going to have to pause this because I can't video. So when we're looking here at this reaction, it's got sodium plus water. Now, I personally would prefer to write sodium solid and make the water an HOH when it is a reactant, HOH. Because it's going to always react as an H plus and an OH minus. Water does not generally react as a hydrogen and an oxygen. Now when it decomposes, it does. Okay, and when you force it to break apart into the elements, it's going to break up in hydrogen and oxygen. But when it just reacts, So this is the replacement of hydrogen in water by an active metal. So we're replacing the hydrogen, not the hydroxide. So we're going to end up getting sodium, which is plus, and hydroxide, which is minus. And then what's the hydrogen going to be? Well, what's hydrogen always going to be? H2. H2 gas. So the bubbling and the hissing that you're seeing is H2. Now they're using fractions again to do this. Now we're going to learn in the next part of this unit why it breaks it apart into the ions, how it dissociates into the ions in the water. Okay, we're going to look at that, but let's balance this in terms of whole numbers. One sodium, okay? But I have two hydrogens going to here. So I have to put a 2 there. Now that gives me 2 hydroxides. So I need to put a 2 there to get 2 hydroxides and then 2 sodiums there. Now it's the same thing as this, just 2, 2, 1, and then a 2 in front of that. But this is the reaction. It's the replacement of hydrogen in water. Water is very, very stable. Water, hydrogen and oxygen, they like being together. They do not want to break apart. But a very active metal like this will actually replace the hydrogen. But it's really just the alkali metals. Now, it's going to get better, okay, as we go on. So so pause my video. So what we saw there, again, was sodium solid, and all the alkali metals did the same thing. All you do is replace sodium with lithium, potassium, whatever, plus water, HOH, okay? And we ended up getting sodium hydroxide, aqueous, and hydrogen gas. And we had to put a 2, a 2, and a 2, and that's a lousy 2. Okay? Now, what's happening? What's the charge on sodium right here? What's the charge on any element in its natural state? 0. Sodium is 0. Now, wants to be +1. When it goes and reacts, so what is this charge here? +1. So how did it get from here to here? What had to happen?
Reaction.
Yeah, but what was the actual reaction? How did it go from 0 to +1?
Taking something from something.
Okay, but I mean, what happened to the sodium itself to go from 0 to +1?
One over the hydroxide.
Okay, but how does something go from 0 to +1?
By adding one.
It lost an electron. It lost 1 electron. Okay? So now we want to try and talk about why did it get so much more violent, so vigorous as we went down. Okay? So when we look at lithium, what would lithium's electron configuration be? It's 1s2, 2s2. What would it be for lithium? 1s2,
2.
2, what?
2s1.
2s1. Then sodium, what's it going to be?
1s1, 2. 2s2.
1s2, 2s2,
2p6.
6,
3s.
3s1. And then potassium is going to, what's its last electron? Where is it going to end out here? Where's potassium going to end? 4s1. And then the rubidium is going to end at 5s1, and cesium is going to end at 6s1. So what does that mean about this electron as far as its distance from the nucleus? It's getting farther away. What does that mean about how tightly held it is? It's getting less and less tightly held, right? And all of them are doing this exact same thing. They're all losing 1 electron. So why do you think the reaction started getting a little more vigorous?
Because they're getting closer. They're
It's easier to lose the electron.
It's so much easier to lose the electron. And so the electrons just come flying off, and so they're all losing them kind of at the same time, and so a whole bunch of hydrogen and heat is being liberated because this electron's coming off way easier than that electron. Now they're all coming off, it's just how easily and how quickly, And the cesiums are just, hey, I can care less. It's not holding that electron. That long distance relationship is easy to break, and so that electron comes off very quickly, and as a result, a lot of hydrogen is produced and a lot of energy is produced, and so boom, we blow up. And notice they only did it once. They didn't keep doing that one because the cesium is kind of rare and expensive.
What happened if you did that with francium?
Now, francium would be even a bigger boom, but there's only about 1 ounce of francium on the Earth at any given point in time because it's got a 20-minute half-life. And so it's only the result, it only gets formed as other radioactive elements decay. And then as it decays, then it's got a 20-minute half-life. So, I mean, it quickly just decays into other things too. So you're never gonna really find or do anything with francium. It's just too rare.
Has it been done before though?
I don't think they're gonna chunk it into water just for fun because it's so rare. But they do, make it in a lab and then test a little bit of the properties, but they don't know a whole lot about it because it just doesn't exist for a long time. So that's the replacement of hydrogen in water, okay, which is, again, your alkali metals are going to do that. Okay. Our last single replacement reaction, golly, time flies. Our last single replacement reaction is going to be the opposite. This time it's the replacement of a halogen by a more active halogen. Which is my most active element? Fluorine, right? So our halogens, the activity just goes down. Fluorine is the most active, then chlorine, then bromine, iodine is the least active. Okay? So again, this is the halogen replacing a halogen. So if I have KCl and I bubble some fluorine gas into it, this time the halogen is going to replace the halogen. So what are we going to make, you think? Kf. Now again, we're going to balance the charge. So what's the charge on K? +1. What's the charge always on fluoride? So it's just going to be Kf. Even though it's F2 here, we don't make it F2 over there. We balance charge first. And then what's my other product going to be? Okay? Cl2. Because chlorine is one of my 7 diatomics. Now this is an alkali metal, so I know it's going to be aqueous. I have to balance it. How do I balance it? I need 2 F's, so I put a 2. I need 2 K's, that gives me 2 Cl's, but there I have 2 Cl's. Okay? Or we could say sodium iodide plus chlorine. What are we going to make?
NCO, sodium chloride.
Sodium chloride,
Plus I2.
Na plus and Cl minus, plus iodine. So I have to balance it again. It's exactly the same way. So they're all going to look, these are all going to look the same, just kind of like the reaction of the alkali metals with water. They're all going to look the same. But it's all, notice on all of these, it's an element plus a compound. Element plus a compound yields an element and a compound. 1 plus 2 yields 1 plus 2. 1 plus 2 yields 1 plus 2. Element plus a compound yields an element and a compound. Okay? Single replacement. Now, double replacement. What do you think happens in a double replacement? 2 things are going to swap. Okay? Now, a double replacement reaction must have a dubious past because it's got all kinds of names. Aliases. Double displacement, ionic exchange, metathesis. But we're going to call it double replacement. Okay? There's 3 types, but they all do the same thing. And I've done some of these before, but if I take some potassium iodide, Ki, Okay? And then I take some silver nitrate. Well, actually, probably that's not what I want. I want lead nitrate. Pardon me. I take some lead nitrate. Okay? So I'm going to take some Ki, aqueous, and put some lead nitrate, aqueous. If this is a double replacement reaction, what do you think it's going to make?
Potassium nitrate and lead iodide.
Okay, so potassium nitrate, so potassium is what charge? +1, and nitrate, we look on the chart, we see that it's, try again, nitrate, again, we don't guess, it's -1,
Just kidding.
okay? Plus, what you have to say, Jackson, was the other thing?
Lead iodide.
Lead iodide, so we say Pb and I, but what's the charge on Pb here? And how do I know? Well, it's going to be +2 because this is -1. They got 2 of them, so it's -2. So it's going to be +2. But also remember, generally speaking, whatever that subscript is, that's going to be the charge. So if it's +2 on the left, it's going to be +2 on the right. So we're going to say 2+. And what's iodine always? -1. So it's going to be PbI2. All right? So now when I put those together, here's the lead nitrate. This is your Ki in the test tube. Here's your lead nitrate. Anybody want to venture a guess as to what's going to happen?
It's gonna blow up.
Okay? I put it in here. Now I'm a trained professional. Do not attempt this at home. Okay? All right? It generally doesn't blow up when I put them together, but
Stop.
anyone want to guess a color? Purple, pink,
Green.
green, blue?
Black.
No color.
Nobody said it yet.
Black,
No
black,
color?
Black,
Okay.
black.
All right, all right. Again, I just, here we go. Okay, it's a real bright yellow. And because it's going cloudy, what does that indicate? A precipitate is being formed. Okay, now I did this yesterday in another class. You can see that this precipitate will settle down to the bottom. Okay, we have the other solution sitting in here. Okay, so it's a yellow precipitate. So now I want to kind of think about, well, which one of these then do you think would be my precipitate? Well, when I look at my solubility chart, remember we said all alkali metal compounds are soluble. All nitrates are always soluble. They never make a precipitate. Okay, so this is going to be aqueous, and by process of elimination, that means this one must have been my solid. Just put them on the pile right over there. On the pile right over there. Okay? So this is, oh, we didn't balance it either. We got to balance this. How do we balance it?
2 in front of the potassium nitrate.
2 here,
Yeah, put a 2.
and a 2 there. All right? So we have a double replacement. This is kind of like, you know, like must have listened to a lot of country music, you know, because they just kind of swap, you know, you stole my wife, so I'm going to steal your husband type thing. But that might be new country. Yeah, they just kind of swap, you know. I always think, you know, I would kind of this. I think of that because Shania Twain. Have y'all ever heard of Shania Twain? Big
I've heard
country
of
singer.
Mark Twain.
She married her producer, okay, and then she has this best friend and they're living up in Canada, and it turns out that her husband and her best friend end up having an affair. So they get divorced, and her best friend and her husband then get married, and so then she begins commiserating with her best friend's husband, ex-husband now. And then they fall in love and they get married. So they actually did the wife swap in real life. You know, it's just real country music going on right there. But that's what happens. That's what happens in a double replacement reaction. They just swap. All right, we're going to finish this up tomorrow. Tomorrow we're also going to talk about what causes this. Y'all have a great day and go Jags.